Good day, sir. I'm Carlos Iwano from BCME. For now, I'm going to discuss about the PVT behavior of gas mixtures, ideal and real gases. First, what is ideal gas? An ideal gas is defined as a gas whose molecules are spaced far apart so that the behavior of molecule is not influenced by the presence of other molecules. A situation encountered at a low densities. So what is real gas? And real gases approximate this behavior closely when they are at a low pressure or high temperature relative to their critical point values. Formula PV equals to ZRT, where Z is the compressibility factor. When two or more ideal gases are mixed, the behavior of a molecule normally is not influenced by the presence of other similar or dissimilar molecules, and therefore a non-reacting mixture of ideal gases also behaves as an ideal gas. Air, for example, is conveniently treated as an ideal gas in the range where nitrogen and oxygen behave as ideal gases. When a gas mixture consists of real non-ideal gases, however, the predictions of the PVT behavior of the mixtures becomes rather involved. There are two models for PVT behavior of gas mixtures. First is Dalton's law of additive pressures. Second is Amagat's law of additive volumes. So what is Dalton's law of additive pressure? It is the pressure of a gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperatures and volume. As you can see the picture, Dalton's law of additive pressures for a mixture of two ideal gases, gas A and gas B. Volume temperature plus volume temperature, pressure A and pressure B equals to gas mixture A plus B, V, and temperature Pa plus pressure B. And the second PVT behavior mixtures is Amagat's law of additive volumes. What is Amagat's law of additive volumes? Amagat's law of additive volumes says that the volume of a gas mixture is equal to the sum of the volumes each gas would occupy if it existed alone at the mixture's temperatures and pressure, which is illustrated in the figure below. And if Amagat's law of additive volumes for a mixture of two ideal gases, gas A, pressure, temperature, and volume A, plus gas B, pressure, temperature, volume B equals to gas mixture A plus B, pressure, temperature, volume A plus volume B. Dalton's and Amagat's laws hold exactly for ideal gas mixtures but only approximately for real gas mixtures. This is due to intermolecular forces that may be significant for real gases at high densities. For ideal gases, these two laws are identical and give identical result. Also, Dalton's and Amagat's laws can be expressed in the equation that we have below, which is Dalton's law and Amagat's law. So Dalton's law formula, Pm equals to K summation of I over 1 times Pi times Tm plus Vm. Also, the Amagat's law formula equals to Vm equals to K summation of I equals to 1 times Vi times Tm plus Pm. Exact for ideal gases, approximate for real gases. In these relations, P ideal is called the component pressure, and volume ideal is called the component volume. Note that volume ideal is the volume component that would occupy if it existed alone at Tm and Pm, and not the actual volume occupied by the component in the mixture in a vessel that holds a gas mixture. Each component fills the entire volume of the vessel. Therefore, the volume of each component is equal to the volume of the vessel. Also, the ratio of P ideal over Pm is called the pressure fraction, and the ratio of V ideal over Vm is called the volume fraction of component I. Therefore, for ideal gases, Pi and Vi can be related to Yi by using the ideal gas relation for both the components and the gas mixture, which is shown in the equation below. The equation is strictly valid for ideal gas mixtures, since it is derived by assuming ideal gas behavior for the gas mixture and each of its components. The quantity YiPm is called the partial pressure, identically to the component pressure for ideal gases, and the quantity YiVm is called the partial volume, identically to the component volume for ideal gases. Note that for an ideal gas mixtures, the mole fraction, the pressure fraction, and the volume fractions of a component are identical. Let's proceed to real gas mixtures. Dalton's law of additive pressures and Amagat's law of additive volumes can also be used for real gases, often with reasonable accuracy. Pm times Vm equals to Zm times Nm times Rn times Tm. Also, Zm equals K summation of over I equals 1. Yi times Zi. Dalton's law disregards the influence of dissimilar molecules in a mixture on each other. As a result, it tends to underpredict the pressure of a gas mixture for a given Vm and Tm. Therefore, Dalton's law is more appropriate for a gas mixtures at low pressures, and Amagat's law is more appropriate at high pressure. Note that there is a significant difference between using the compressibility factor for a single gas and for a mixture of gases. The compressibility factor predicts the PVT behavior of single gases rather accurately, but not for the mixture of gases. When we use compressibility factors for the component of a gas mixtures, we account for the influence of like molecules on each other. The influence of dissimilar molecules remains largely uncounted. Consequently, a property value predicted by this approach may be considered different from the determined experimental value. Another way of predicting the PVT behavior of a real gas mixture is to treat it as a pseudo-pure substance with properties P9Cr and T9Cr. So pseudo-pure substance P prime Cr times M equals to K summation of and I equals to 1 Yi times PCr I. T prime Cr times M equals to K summation of I equals to 1 Yi times T Cr times I. And that is all. Thank you.